All right. All right. Good day, team. Good day. Welcome to Unit 1, Day 5. We're going to be finishing up our very first calculus unit today. Welcome to Day 5. Miss Bowman rambles on for about 45 minutes to you. I hope you enjoy it. So we kind of have some goals, some objectives for the day that we're going to be talking about to finish up our limits unit. We're going to kind of go back today to where we started on day 1, and we're going to talk about how do we calculate like the average rate of change of a function and the instantaneous rate of a function. And then we're going to talk about some equations of lines that you may have seen before. It'll sound kind of familiar. You probably remember them from Orchard Hideout. There's secant lines and tangent lines, and we're going to discuss normal lines. So at the beginning of the unit, we kind of introduced this idea of limits using the idea of average speed and instantaneous speed. And we're going to kind of go back to that and just kind of generalize it through all functions as opposed to just speed. We're just going to talk about the rate of change of functions. You've done this in Small World, but what you were doing in Small World was kind of approximations. And today we're going to actually calculate instantaneous rates of change and average rates of change. And so forth. So we're going to go through and start. Again, I'm going to ask you to pause at different times to try the problems on your own. We'll go over the problems, and then any tough stuff I'll probably go over again in class just to make sure that we're all on the same page. You can follow along. We're on Unit 1, Day 5 in your notes packet so that you have space and the problem's already written out for you. If you're doing this in your notebook, totally fine. I'm going to try to not say a million times, which I just counted like 6 in the last minute, so we'll see how that goes. But let's go ahead and get started. So we're going to first talk about average rate of change. So in general, the average rate of change of a function over an interval is the amount of change in the function's value divided by the length of the interval. In other words, it's the change in the value divided by the change in the domain, or the change in the height divided by the change in the domain. It's kind of like a general slope. So to find average rate of change of a function, we take the change in the function's values. Help if I have a marker. You know what? I'm feeling kind of fancy today, guys. I think I'm going to go calligraphy pen. So it's going to be, that's a little too thick though. We're going to go change in the values of a function over the change in the interval or the length of the domain. So you can kind of remember this is just the y values or the heights, the change in height over the change in length, okay, on the interval a to b. So if I had a function that looked whatever, and here's b and here's a, and I found the rate of change of that function, what I've done is I've said, okay, what is the overall change? So if I were to look and make it a straight line, a linear function between those two endpoints, what is the rate of change of that line? So this line in calculus and in mathematics in general that is defined by 2 points on an interval is what's called the secant line. Okay, so this is the secant line. And the average rate of change of a function is also just the slope of the secant line. So it's the slope of the secant line or secant line. I say that word funny because of my southernness. Secant line, okay, is the average rate of change. And I'm probably just going to call it refer to it as AROC from here on out. Feel free to write it as AROC. I'll know what you're talking about. Okay. So we're going to try just a couple of two questions. So this first example, find the average rate of change of f of x equals e to the x plus 5x over 0 to 1. So go ahead and pause me. Try to find the average rate of change on this interval, and then we're going to go through and talk about it. So pause me. Okay, I'm back. You unpaused me. Great. So now we're going to go ahead and do this average rate of change. Now, I will tell you on the AP exam, we're going to talk a lot about the AP exam. I've been teaching calculus for, 13 years maybe, and teaching for 16. So this is my 16th year of teaching, and I've been teaching calculus for the bulk of those years. I think there's maybe only 4 years total that I didn't teach it, so 12 years I've been teaching it. So I know the AP exam. I'm comfortable with the AP exam. I'm going to tell you what the expectation is for the AP exam. throughout the course of the year. You're going to be very familiar with it. A lot of the practice we do will be old AP stuff, typical of any AP class that you take, but we're going to do it from the context of calc. So in calculus, one thing to note about the AP exam is there's 3 questions that they can ask you. What are you doing? How are you doing it? Why are you doing it? All 3 of those, the what, the why, and the how, are equally important to that. So what I mean by that is a lot of times if you set up a problem, that tells them that you know what you're doing, even if you don't know how to do it. So this statement that I just wrote here literally earns me a point on a free response question because it is the setup of average rate of change. Now, I haven't plugged it into the function at all. This is what I call the save my butt step. And the reason being is because we tend to tweak a lot, and we like add wrong and subtract wrong, and that's just going to happen to us for the rest of our lives. And there's no shame in that game. But if we're talking about getting points on an AP exam, we need save our butt steps, and this setup is a save your butt step. So now I'm just going to plug 1 into my function. So I get e plus 5 minus, now I'm going to plug in 0. So e to the 0 plus 0. Be careful here because e to the 0 is not 0. E to the 0 is 1. So I end up getting e plus 5 minus 1 over 1, which is just e plus 4. And I'm just going to leave my answer. Now, if somehow I would have tweaked and said e to the 0 is 0, I would have gotten e plus 5, which is the wrong answer. And I would have lost 1 out of 2 points. But because I had my setup step, I still got 1 out of 2. Now, if you went straight to, let's say, this step, and you put in or you went straight to this step, but you had a 0 here, you would get 0 out of 2 because you don't have the right setup either. So just a little warning, we're going to talk about setup a lot. So the other thing I'm going to note is that there are 2 types of questions, calculator questions and non-calculator questions on the exam. We are going to assume most of these are going to be non-calculator, so we're going to leave things exact. If you do end up getting a decimal approximation, first of all, I'm going to use my approximation symbol here instead of my equal sign, and I'm going to put 6.718. So one thing to note for calculus is that it's always going to be 3 decimal places for any decimal approximation that you use. Okay. All right, example 2. So now find the equation of the secant line from 0 to 4 through the function f of x equals x cubed minus 2x squared plus 7. So go ahead and pause me, see if you can come up with the equation of the secant line. Unpause me, and I'll go through the answer. I'm going to take a sip while you're pressing pause. Okay, so let's go through this one. Now that you've tried it on your own, I'm going to say that 100 million times. And I know people are just listening straight through, and I sound ridiculous if you do. So first, what we need to do is find the slope of the secant line. So if I want the slope of the secant line, I'm just going to put like m secant to represent it. That's just the average rate of change. The average rate of change of our function is the slope of the secant line. So I'm going to do f of 4 minus f of 0 over 4 minus 0. And again, I'm writing that step. Is this step necessary? No. Will it save you when you can't add right? Absolutely. So I'm a big fan of it. But again, if you went straight to some sort of difference quotient or some sort of slope formula and you had already plugged in 4, then you would be fine here. So I'm going to plug in 4. 4 cubed is 64 minus 2, let's see, 4 squared is 16 times 2 is 32 plus 7 minus, now if I plug in 0, I end up 0 minus 0 plus 7. You see how I put those in parentheses just to make sure. So I get 39 minus 7 over 4, which is 32 over 4, which I can actually reduce into a nice number 8. Sometimes they're nice, sometimes they're not. Now, I just found the slope of the secant line, and a lot of people will think they're done here, but just be careful because it says find the equation of the secant line. Now, here is my soapbox, guys. If I ask you to write the equation of a line, and I don't specify what type of equation to write, I highly recommend writing it in point slope form. Now, this one is nice because we do have the y-intercepts because we know we have the point 0, 7 and the point 4, comma 39. I got that from plugging them in. So I do have the y-intercept to go straight to y equals mx plus b. but I just like to put it in the habit of putting things in point slope form. So I'm actually going to use my second point, y minus 39 equals 8 times x minus 4, just to kind of switch things up with you. You could also have y minus 7 equals 8 times x minus 0 if you want to write that in point slope form, or you could have y equals 8x plus 7. Any of those equations are going to work. Point slope form is going to be the fastest way to do what they ask you to do and move on. Solving for b, if you don't have the y-intercept, can get really annoying, especially with fractions involved. So point slope form is your best friend. Okay, I'm going to stress that a lot. Okay, so let's look at this next example. How do we measure velocity? Well, what is velocity? Velocity is rate of change plus direction of an object in motion. So if here we go, a hot air balloon is rising and falling as shown by the graph at the right. Estimate the average rate of change of its height on the following intervals and draw the secant line through the endpoint. So I'm going to go ahead and ask you to pause me. I'm going to put little meters there. Pause me and try these 3 questions that are here. And then I'm going to go through them after you unpause me, because you're totally pausing me right now. Okay, so let's go through what you did while I was on pause. If I want the average rate of change, here we're going to do f of 20 minus f of 0 over 20 minus 0. So f of 20 is right here. F of 0 is right here. The secant line would be this line. I can see here if I estimate that, I have about 20 minus, I don't know, we'll go 127 over 20, which is negative 107 over 20. I'm going to leave it like that, but I'm going to make sure that I put units on, because they're always going to grade my units in a situation. Okay, from 8 to 15.5. So 15.5 is like right here. I couldn't have picked nastier numbers, could I? And then 8 is right here. So I can see this would be my slope. And if I want to estimate that, again, I can do the save my butt step by just setting this problem up. I've earned a point on a free response question by writing that statement. But then once I got to do it, I am going to see here, let's go about maybe 52 minus 65 over 7.5. So I got negative 8 over 7.5. Oh, wait, negative 13 meters per minute. The fourth one, I'll do that one in red just to switch up the color. So we got at x equals 4. Here's my point. At 12, here's my point. The secant line would be right here. So if I want that average rate of change, I'm just going to do f of 12. Ooh, why is that so thick? Let's go ahead and make that better. Minus f of 4. There we go. Over 12 minus 4. Let's see. F of 12 is about, let's say, 98. F of 4 is like 48. Over 8. That gives me about 50 over 8 meters per minute. So there's some good secant line practice, some good average rate of change, some AROC practice. So again, average rate of change is just how on average the function is changing. The height is changing for every given x. It is the slope of a secant line, and then the secant line is the line through the 2 endpoints. Okay, so we're going to look at one more. Oh, I skipped ahead. And we're going to kind of move into this idea of instantaneous versus average. So again, if I'm finding velocity, velocity is a rate of change. It's like a speed plus direction. So if you notice in this last example, we did have some answers that were negative, part A and part B. Velocity can be negative. It just means that it's moving backwards, okay, or moving down depending on the situation. So here, a ball was thrown in the air, and its height is modeled by the function h of t equals negative 3t squared plus 30t. Find the average velocity from 2 to 7. So here I see that I have a height equation, that this is measuring height over time, but they're asking me for the average velocity. So that's just asking me, a fancy way to ask me for the AROC. So to find the AROC from 2 to 7, I'm going to do h of 7 minus h of 2 over 7 minus 2. So I'm doing the change in position over time, and that'll give me the average velocity. And this, my units are going to be feet per second. So here, if I plug in 7 into my function, I'm going to get out 63. If I plug in 2 into this function, I'm going to get out 48. So 63 minus 48 is going to give me 15 over 5, which is just 3 feet per second. And again, that would just be if I drew the 2 points between 2, whatever 2 is, and 7 is, and I found the slope between those 2 points. Now, part B is a little bit different. It says estimate the instantaneous velocity at t equals 6. So now it's not asking me for a rate of change at 2 points. It's asking me for the rate of change at 1 point, which we kind of did on the first day of Unit 1. But let's kind of talk about the difference between what we did then and what we're going to do now. This is asking us to estimate the instantaneous velocity. So this is kind of like what you did in Math 3 in the small world unit. If I want to estimate the instantaneous rate of change, okay, I'm just going to take 2 points, one of which is 6 and one of which is really, really close to 6. So you could go from like 5.999 to 6, or 6 to 6.001, or from 5.999 to 6.001. However you want to do it, I'm going to go h of 6.001 minus h of 6 over 6.001 minus 6. And when I use my calculator with this function, which is what I did prior to this, I end up getting an answer that's approximately negative 6 feet per second. So I can say the instantaneous velocity at time equals 6 of this ball is approximately negative 6 feet per second. I can't say it is exactly, but I can say that it is approximately. Okay, so there's a little bit of difference here. Because I used a decimal 6.001, I am now approximating the instantaneous velocity. Now, if I were to try to show you what I just did, I took a point at 6 and a point at 6.001, which is right next to it, and I drew a line that kind of touched it. So if I look at this line that touches a function at a single point and has the same slope, like the slope of this line is negative 6, that is what we call a tangent line. So some vocabulary for you. A secant line is a line passing through 2 points on a curve. It uses an AROC. The tangent line is a line that touches the function at a single point and has the same slope as the IROC at that point. So if I'm drawing a line at x equals 2, whatever the slope of the function is at 2, the slope of my line should be at 2. So let's see if we can find the example for our secant line that goes through 2 and 7. So again, I'm going to use point slope form here, and I know when I plug in 2, I get out 48. I just chose that point, and I know my slope from my AROC from before was 3. So I'm going to go y minus 48 equals 3 times t minus 2. And I'm going to use t instead of x only because they use t in the thing as well. Okay. Find the equation of the tangent line through t equals 6. Now, in order to write the equation of a line, you need a point and a slope. The slope we got from our approximation. So my slope for my tangent at 6 is negative 6. The point would be 6 comma whatever happens when I plug in 6, which I'm pretty sure is 70, if I remember. Let me just double check that. 72. So if I were going to do that, then I'm going to say y minus 72 equals -6 times t minus 6. So that would be my tangent line through t equals 6. Okay, so we have a secant line, a tangent line. Writing the equation is the same. All you need is a point and a slope because we're going to use point-slope form forever and always for the rest of your life. So for the rest of class, I'm going to kind of focus on tangent line equations in the IROC, and then we'll kind of finish up with a little talk about another line called the normal line, coming from the Greek normalis, which we'll talk about what that means and where it comes from. But I want to clear some things up with tangent lines because they tend to be confusing. So how you've seen tangent lines before is with the following situation. In Math 3, tangent lines were used in the context of circles. So we say that this line is a tangent line to point P because it touches the function at a single point P and has the same slope as the slope of P. So if I were to take that line away and kind of imagine what the slope would be at that point, or the steepness of the function, this line and this point P have the same slope. So a tangent line touches the function at point P and has the same slope as point P. So I'm going to show you 4 pictures, and I want you to kind of look at each one and decide, is the line L that I've drawn a tangent line to point P? Okay, so that's your question. Pause me, see what you think, yes or no. The worst thing that happens in the world is that you're wrong, and if that's the worst thing that happens to you today, I'd say you're living a pretty good life considering there's a pandemic, okay, team? So don't be afraid to make mistakes. Again, we're going to make a ton in this class. That's the beauty of the class. We're gonna learn through them. So look at these 4. What do we think? Is line L a tangent line to point P? All right, you've had time to think because you paused me. So now, if we look at this first one, the answer to this one is no. Even though line L touches point P on the function, if I look at the function itself, the slope at point P is a negative slope and line L goes through it. So this is not a tangent line because it's not the same slope. Now this one is where the little debate comes. So if I look at point P, does line L touch point P? Yes. Does line L have the same slope as point P? Yes. Is it a tangent line then? Yes. Does it touch the function other places? Yes, and that's okay, because what we're asking for is, does it touch just at point P and have the same slope as P? Then we say it's a tangent line to P. This is okay. The fact that it hit it again is totally fine because we're just worried about what's happening around point P. Okay, third picture, is this line L a tangent to point P? Nope, not the same slope. And this one is interesting. So here's point P, and if I look at the function, point P and line L have the same slope, but it appears that line L touches the function lots of places. And all that is because of pixelation, because I can't zoom in close enough to see. So this one is still yes, because it touches point P and has the same slope as P. Therefore, line L is a tangent line to P. So it can touch the function other places, but it has to touch P and it has to have the same slope as P. So they have to share that point and share that slope. Okay, so a little bit about tangent lines. So now, the question is, your whole mathematical career since Math 3, you've talked about instantaneous rate of change. And from here on out, I'm probably going to refer to it as the IROC instead of the AROC. So the instantaneous rate of change is the rate of change at a given point. All you've done is approximate it because you've taken 2 points and kind of found the slope of like 6 and 6.001. So even though 6.001 is basically 6, it is not the same thing. So we're going to kind of go on a little mathematical journey, going back to what we did on day 1 to kind of talk through how do we find the instantaneous rate of change of a function. So here's our idea. to find the instantaneous rate of change, to find the IROC, and to not estimate it. So we're going to actually figure it out exactly without estimating. The problem, let's say we wanted it at x equals a. If I found the slope between a and itself, which is what I would want to do, I end up with 0 over 0, which is an indeterminate. So what we want to do is we want to do this, but algebra has failed us in this case. So what we do instead is kind of use the idea of how we approximated it, except we're not going to define the distance. So in the previous example, I did the slope between 6 and 6.001 because 0.001 is a really, really small distance away from 6 that I can use, and it won't give me a 0 over 0. So what we're going to do is we're going to pick a point h spaces away. And find the AROC. Now you're like, what does H represent? Oh, that should say AROC. H, for our intents and purposes, is going to represent a really, really, really small distance. So what we would need to do then is we're going to find the slope between a point A here. So here's A. And then I'm going to go H spaces away from A and name this point A plus H. Okay, so we have a point at A and a point at A plus H. And I'm going to say this is x equals A and x equals A plus H. I don't know why I put A plus H in parentheses. It doesn't have to be. So here's the idea. I want to find the slope between these 2 points because we can only pick 2 different points to find the slope between, because if it's the same point, we get 0 over 0. So I'm going to pick 2 different points. Now, what I'm going to do is I'm going to say, okay, I can't actually have no distance between those points, but I want to find the intention if that distance decreases till nothing. So we're going to find the intended value of the slope as the distance draws closer and closer and closer until there is no distance between the 2 points left, which means that H value is going to approach 0. So technically, if H is 0, we would have f of A minus f of A if I was finding the slope. So to find the IROC, we're going to find the slope between the point A comma f of A and then A plus H. I can tell when my surface gets laggy because my handwriting decreases. A plus H. Okay. So we're going to find the slope between those 2 points. So that's the first step. I'm going to leave some space over here on purpose. So I'm going to go f of A plus H minus f of A over A plus H minus A. Now you're like, Ms. Bowman, can I simplify that denominator? Absolutely. Those A's are going to cancel, and it's just going to leave you H on the bottom. Now, some of you are like, wait a second. I know what that is. We did that in Math 4 all the time. That is the difference quotient. Yes, you're right. And the reason why you did it in Math 4 all this time was for today's lesson. Congratulations. Math 4 is a prereq for calculus. You needed that skill to be able to interpret it in this meeting, but that's neither here nor there. Now, writing it like this, I've actually found an average rate of change. I found the average rate of change between a point A and a point that's H spaces away from A. Now, I can't make that H be 0 because, again, if it's 0, I end up with this problem case over here. But what I can do is I can find the intended value as H approaches 0. Now, that's the key part here, and you're like, I was wondering when limits were going to come into play. So what we're going to do is we're going to say, okay, we have distance now, and we want to limit that distance. So we're going to take the limit of that slope as H approaches 0. And that, my darlings, is the definition of the exact instantaneous rate of change of a function. We do no longer have to approximate it. We just have to do the limit of an AROC. Okay, so we're no longer going to do 6.001 and 6, even though that's a good estimation. We're actually going to calculate the exact. So IROC is a limit. It's the limit as the distance between 2 points approaches 0 of the slope between those 2 points. So again, h just represents the distance between those 2 points. And then if we want to get a tangent line, well, the IROC is the slope of that point, which means it's the slope of a tangent line. So what this will do is it gives us the slope of the tangent. Oh, come on, lag. Gives us the slope of the tangent line. I'm just going to quit writing here in a second. Okay, that's about as good as it gets. Okay. And then to write the equation of a tangent line, what do you just need to figure out what's the IROC and then do point slope form. So what's your point? What's your slope? Write your equation. Okay. So we're going to do a million examples of this. Not actually. I'm going to go through 1, 2, 3, 4 examples of the tangent line. Feel free to skip through any if you feel like you've got it. I'm just going to do some more complicated ones as we go through. And then we're going to talk briefly at the end about the normal line and what does the normal line mean and how do we find the normal line. And it's really not that difficult. That's a spoiler for you. If you can get the tangent line, you can get the normal line. So I'll explain that. So let's go through some examples of how to write the equation of a tangent line. It's right here. Here's my example 7. So y equals x squared plus 2 at x equals -1. So if I want the equation of the tangent line, I got to think to myself, I need a point and a slope. So the point I would get by just plugging -1 into my function. And I get out 3. So my point is -1, 3. So I'm going to use that point for my point slope form. Now I need my slope. So slope of a tangent, that's asking for the IROC, not an AROC. So IROC, if I want my slope, the IROC is a limit. And what happens is if you don't write that limit notation in the front, you're going to lose all points on your setup and your answer because you don't know what the IROC is. So the IROC is the limit. So what we're going to do is we're going to find the slope between -1 plus h and -1. So I'm picking a point at -1, and then I'm picking a point at -1 plus h, and then I'm putting them in. So this is the definition of the IROC. So I would get all the points for setup right here in that little expression. And again, if you just want to know that those cancels and you just have h on the bottom, that's totally fine. So I need to plug -1 into my function. Notice that as I'm doing this procedure, that my little h limit notation follows me. And it's not the limit as x approaches 0. We're limiting the distance between 2 points, which is what's known as h. So I'm going to plug -1 plus h into the function minus, I'm going to plug -1 in, which I already did earlier, so that's kind of nice. So I just have -3 all over h. And then I'm going to keep simplifying and taking this limit. So I end up with let's see, -1 squared is 1. -1 times h doubled is -2h. H squared is just h squared. Plus 2 minus 3 is -1. Now, if I were to go ahead and plug in 0, I am going to get 0 over 0. So I'm going to keep cleaning this up. And that's kind of the trick here with this limit, is that you want to keep cleaning it up. So the 1's are going to cancel, and I end up with -2h plus h squared all over h. Now I can see here, if I were to plug in h with 0 to actually take the limit, I would still end up with an indeterminate. So what we can do is just either factor the h from the top, or since this is shaped like a heart, I like to break the division. That's like my trick. So I end up with negative 2h divided by h, which is negative 2. H squared divided by h is h. So I've simplified the slope expression. I've simplified the difference quotient as much as possible. Now your last step is to actually take the limit. So if I take my limit here, if I plug in 0 for h, negative 2 plus 0 is just negative 2. So there's my slope. And once you get your point and your slope, then it's just a matter of point-slope form. So y minus the y equals the slope times the quantity x minus the x. And that is the equation of the tangent line to that graph x squared plus 2 at x equals negative 1. And if you think about if this makes sense, x squared plus 2 looks like this. If I look at negative 1 and draw that tangent line, it should have a negative slope. That seems about right, that it'd be negative 2. Okay, so that's your first example. So the rest of them, I would say, pause me, try them, and unpause me for the solutions, okay? And again, if you're just like, I'm over this, I need to take a brain break, that's why I record these, so you can kind of take your brain break and come back when you need to. The next couple of examples are just trickier algebraically, but it's the same idea. So I just want to make sure that I go through some, since I have unlimited time videoing stuff, that I go through how to do these harder ones algebraically so that you have them to reference, okay? So let's see, for the function f of x equals 1 over x minus 1, find the instantaneous rate of change at x equals 2. Okay, so I like to set this up. What I actually do is I'll go, what is f of 2 and what is f of 2 plus h? So I go ahead and like find those expressions to make my limit work and my difference quotient a little bit easier. So if I plug in 2, I get 1 over 2 minus 1, which is just 1. So I have the point 2 comma 1. If I plug in 2 plus h, I'm going to get 1 over 2 plus h minus 1, which can simplify into 1 over h plus 1. So I have the point 2 plus h, comma, 1 over h plus 1. So now I'm going to set it up. Notice how it starts. Without this, you get nothing, folks. So I'm going to do y2 minus y1 over x2 minus x1. Again, those 2's are going to cancel. Now, if I were to go ahead and plug in 0, I am going to get 0 over 0, so I know I got to clean this up. So now the question is, what do I do from here? And there's a couple of different strategies that people use to simplify complex numbers or complex fractions, which is what this is. What I'm going to do is I'm going to multiply the top and the bottom by h plus 1 because that is the common denominator. You'll see kind of why I do this in a second. So now I have the limit as h goes to 0. And if I go ahead and distribute this in, 1 over h plus 1 times h plus 1 is just 1. Minus 1 times h plus 1 is just h plus 1. Notice how I put it in parentheses. All over h times h plus 1. And I always leave stuff factored because I know I got to cancel something out. So that gives me the limit as h goes to 0 of, if I go ahead and distribute this, 1 minus h minus 1. So I go ahead and distribute that in so I don't mess up. That's just going to leave me with negative h over h times h plus 1, which I can see here, those h's will cancel. So I have the limit as h goes to 0 of negative 1 over h plus 1. So I've simplified my complex fraction as much as possible. Now I'm actually going to do the last step, which is to take the limit. So to take the limit, I'm having h approach 0. So I'm just going to plug in 0 for h. And what that does is give me negative 1 over 1, which is just negative 1. So I did all that work just to get a slope of negative 1. So now to write the equation line at 2, the equation of the tangent line at 2, it's actually easier because I have the point 2 comma 1. I have a slope at that point of negative 1. So it's just y minus 1 equals negative 1 times the quantity x minus 2. And that would be the equation of your tangent line. Okay. So that's a little bit of a harder one. And then to go into a little bit of a trickier one, let's look at this problem 9. And then we'll talk about when do tangent lines exist? When do they not? Okay. Find the slope at x equals a. So I'm going to follow the same point here. I know I'm going to have the point a, and I'm going to plug a in, and that gives me 2 over a. And then I'm going to plug a plus h in, which actually just gives me 2 over a plus h. So I have my 2 points, and now to find the slope at a, I'm going to take the limit as h goes to 0. So again, no matter what variables or whatever is happening in the IROC process, it's always h approaching 0. I know the bottom is just going to be h. So then I'm going to have 2 over a plus h minus 2 over a. And again, if I were to plug in 0 right now from h, I would get 2 over a minus 2 over a, which is 0 over 0. It's an indeterminate. So I need to simplify this complex fraction. So now the common denominator here for the numerator, because that's the part that has fractions, if I have a plus h and a, I have to multiply them together because they don't share any common factors. A plus h has to stick together because of the addition. It's not that I can just multiply this one by h. So what I'm going to do is I'm going to multiply both the top and the bottom with a and a plus h because that would be the common denominator. There's other ways of simplifying these that you might be more comfortable with. This is just the way I found is the fastest for me. So when I do that, I just distribute this to both terms. So I'm going to multiply that into this one and multiply that into this one. So in the first one, the a plus h's cancel, and it just leaves me with 2a minus 2. And then with the second one, the a's cancel. So it's just going to be 2 times the quantity a plus h over h times a plus h. And again, I just leave all those factored out. And what's nice about doing it this way is that you get rid of the fraction pretty instantly, and you don't have a lot of you get rid of the complex part pretty instantly, and now I just have a fraction to clean up. So if I clean this up, I end up with 2a minus 2a minus 2h over ha times a plus h. I can see these 2a's cancel. And then I can see I have a negative 2h on top and an h on bottom, so that's going to cancel. So I end up with the limit as h goes to 0 of negative 2 over a times a plus h. And now I'm actually going to take the limit. So the limit says the h has to approach 0. So I'm just going to replace 0 with h, and that's going to leave me with a times a, or a squared. So what I've just done is actually just kind of come up with a formula that I can use to find the IROC of any point on that function, which we'll get into a little bit next unit. Part B here says at what values of a does the slope equal 1/2? So now I have a slope expression. I know the slope at any point can be found by doing negative 2 over a squared. So I just want to think to myself, when does that equal negative 1/2? So if I use this, I'm going to multiply both sides by a squared and 2. That's going to give me negative 4 equals negative 1a squared. So a squared equals 4, which means a equals plus or minus 2. So if I plug in 2 or negative 2 as a and I do the IROC, I'm going to get negative 1/2 as the slope. Okay. Whew. Last one talking about the IROCs, and then we're going to finish with the normal line. So if you've hung out this much, I applaud you because my voice is tired, and I know you've been listening for a while. Okay, does f have a tangent at 0? Okay, so first, this is a piecewise function. Here's what I need you to remember. A tangent line has an instantaneous rate of change. Instantaneous rate of change is a limit, okay? How do you know a limit exists? The limit from the left has to equal the limit from the right. So what we're going to do here is we're going to figure out, first of all, what's f of 0, because that's the point of tangency. So if I plug in 0 to the part that includes it, I end up getting 2. So I know f of 0 is 2. Now what I'm going to do is I'm going to find the instantaneous rate of change coming from the left and the instantaneous rate of change coming from the right. So if I want to find the left side, I'm taking the limit as h approaches 0 from the left of f of 0 plus h minus f of 0 over h. So now if I'm doing that, I'm going to think f of 0 is 2 no matter what side I'm coming from. So when I do this, I know this is going to be a 2. 0 plus h to use from the left, though, I am going to use the left side to plug in 0 plus h, since h is arbitrary anyway. And 0 plus h is just h. So I'm actually going to plug it into the left expression. And I end up with that expression. So now if I simplify it, I have the limit as h approaches 0 from the left of these 2's will cancel. And then if I break my heart, I end up with negative 2 minus h. So I end up taking the limit. Now, just because I'm coming from the left doesn't really make a difference. I'm still approaching 0 as the value, so you're still going to plug in 0. Okay. Now, if I want to do the right side, that's going to be the slope of the function coming from the right. So now I'm going to do f of 0 plus h, which I'm just going to write as f of h, because I don't want to write 0 plus h anymore. Okay, but now I'm coming from the right side, so I'm going to plug h into my right side equation. Ooh, Miss Bowman almost lost her points because she forgot to write the limit in front. Okay, so the 2's cancel, then the h's cancel. So I get the limit as h goes to 0 of the function 2, which is a constant. So that limit, no matter where I'm at, is always going to be 2. So if you can see, the slope coming from the left at 0 is negative 2, but the slope coming from the right is 2. So the answer is no. The limit as h approaches 0 from the left of f of a plus h, or f of h minus f of 0 over h does not equal, gosh, lag, there we go, the limit as h approaches 0 from the right of f of h minus f of 0 over h. Ooh, just doesn't even look like English. Okay, so you'll have a problem like this. Now notice that no matter what, though, when I did the right slope or the left slope, I still use the actual point. So even though the left side didn't include 0, I still use the point of 0, 2, because that's the actual point. So no matter what here, you need to use the actual point. It's just the second point is going to come from either the left side or the right side. But the first point should just be what the point is no matter what. Okay, so that's kind of how you prove if a tangent line exists, the slope from the left has to equal the slope from the right. All right, last thing. You've held out this far. We got about 3 or 4 minutes left of of stuff to talk about, and then we'll be done for the day. Okay, so secant line. Let's review. Recap. Here we go. Secant line deals with the AROC. It's the line between 2 points on an interval in a function. Tangent line is the line that goes through 1 point and has the same slope as that point. It deals with the instantaneous rate of change. The normal line is, by definition, the line that is perpendicular to the tangent line. So this is the line perpendicular to the tangent line at a given point. We looked it up of why it was called normal one year, and it has something to do with the Greek word normalis, which talks about right angles. Okay, so for instance, if I had a function, and this is point P, and this is my tangent line, my normal line would be here, because it's the perpendicular. So if this is the tangent at point P, this is the normal. Okay, so it has the same point as the point on the tangent line, but the slopes are going to be different. And to get the slopes, you just have to remember what's true about perpendicular lines. And perpendicular lines have the opposite slopes. So the slope of the normal, I'm just going to put norm, is the opposite reciprocal of the slope of the tan. But the point they share is the exact same. Okay, so we'll do one example of this. Find the equation of the normal line of f of x equals x squared plus 2 at x equals -1. So if I want the equation of the normal line, first I need to figure out what the point is. So if I plug in -1, I get out 3. Now I need to figure out what my slope is. In order to do this, we would need to first find the IROC, or the slope of the tangent, which I picked this one on purpose because we already did it. So we know from example, I feel like it's example 7, that the slope of the tangent was equal to -2. So what that tells me is the slope of the normal would be equal to +1/2. So I have my point already. I have my slope now because I already did the tangent. Here would be the equation of your normal line. Okay. So that's the normal line in a nutshell. So the secant line, the tangent line, the normal line. The last thing I just kind of want to ask you is to look at these 4 statements and figure out which of these have the same meaning. So take a moment, pause me for a second, think through it. Which of these have the same meaning? Okay, the slope of the tangent line to y equals f of x at x equals a. The instantaneous rate of change of f of x with respect to x at x equals a. The slope of f of x at x equals a. The limit as h approaches 0 of f of a plus h minus f of a all over h. Guess what, guys? They all mean the same thing, okay? So if I ask you for the slope of a function at a point, it is the same thing as asking you for the slope of the tangent line at that point. It is the same thing as asking you for the instantaneous rate of change of that function at that point. It is also the same thing as asking you for the limit between f of a plus h and f of a, which is our point, as h approaches 0. So they all mean the same thing. You can see any of these 3 as directions that tells you to do this. Okay, so congratulations, guys. You have just watched your last hour and 15,000 minute long lecture on the Unit 1 on limits. So we'll be talking about this in class, kind of reviewing it, going through some problems together, clarifying things. I hope you enjoyed it and have a great rest of your day, whatever it is that you are doing.